All right, I'm gonna go pretty quick through this one, just because we don't have a lot of time. So here we go. This box is being pulled, 80 Newton force, 50 degrees. All right, so let's get our force diagram here. We've got force of gravity going down, Fg. We've got the normal, or not the normal, I'm gonna say the applied force, 80 newtons, Ft1. All right, there is gonna be a normal force of some kind. Now I'm making it short just because I kind of know what the answer is gonna come out to be. There's no friction, right? So that's kind of curious how that is looking. I'm gonna draw Ft1x in here and Ft1y as dashed vectors because we might want those later. And you can put those on your force diagram. You don't have to though. So calculate the weight of the box. Fg equals mg. So that's 15 kilograms times about 10 newtons per kilogram. So Fg is about 150 newtons. Now, note that that is negative when we put it on the force diagram. The weight is simply the magnitude of the force of gravity. We make it negative when we put it on the force diagram or we set up Newton's second law. X and Y components of the angled force. Okay, I'll redraw it over here. Okay, that'll be Ft1x. That'll be Ft1y. That's 50 degrees, 80 newtons. So Ft1x is 80 newtons times the cos of 50. Ft1y is 80 newtons times the sine. Times the sine of 50 degrees. All right, so calculator. It's in degree mode, 80 cos of 50, 51 newtons, and 80 sine of 50, 61 newtons. Great. Record Newton's second law equations for x direction and y direction. So Newton's second law equations always start off with F net equals ma. Now, how can I write the same equation for x direction and y direction? Well, we actually have to treat the forces and the acceleration separately. So ay, f net y, f net x, ax. I know that this is 0 because there's no vertical motion at all. All right, so that has to be 0. This equals, so ax is really our acceleration of the system. So we can look at the axes now. So let's start in the x direction. What forces do we have acting in the x direction? Well, only force we have is the x component of Ft1. So Ft1x equals max. In the vertical direction, we have a whole bunch of forces, right? We've got Fn, we got Ft1y, and we have the force of gravity, all adding up to equal 0. Using the appropriate Newton's second law equation, calculate the acceleration of the box. Well, that one's the appropriate equation, so Ft1x is 51 newtons equals 15 kilograms times ax. So ax equals 51 newtons divided by 15 kilograms. 51 divided by 15 is approximately 3.4 meters per second squared. Now, note that it didn't ask me for the normal force. I'm thinking I'm going to calculate that anyways, though. So Fn plus Ft1y, so that is plus positive 61, plus Fg, which is negative 150. You have to put the signs on these in this equation when you do it like this, when you say they all have to add up to 0. And you do the math and you get Fn only has to be equal to 90 nope, 89. Knew there was an 8 in there. 89 newtons. So you bring the 150, so you have positive 150. Bring the 61, negative 61. 150 minus 61 is 89 newtons. Didn't ask it for that, but I figured I'd do that anyways for fun. All right, so good problem. The next one is kind of a nice one. All right, a couple things right out of the gate. Let's do our force diagram. Still frictionless. FG, the applied force isn't nearly as steep. We'll call that FT1. We are still going to have a normal force, Fn. Actually, if you look back at the first question, I can tell you now why I made that shorter, because I knew it was going to come out shorter. In fact, actually, it should be longer than, should be higher than FT1. But anyway, it doesn't really matter at the end of the day. Determine the mass of the box. Okay, so look at, we got the acceleration already in the given problem. A, we don't know the mass. Okay, we know the FT1 is 200 newtons. All right, let me put my components on here. FT1x, FT1y, and I just kind of try to draw them so you can see them. You know, whether or not they're right on the line, that's okay. You know, I just want to draw them so I can see them. All right, so F net equals MA. All right, that's where we have to go here. I know it's accelerating to the right here. It's this horizontal component here that's doing all the acceleration. So the net force accelerating is FT1x equals MA. And that's going to be 200 newtons times the cos of 30 degrees equals m times 2.5 meters per second squared. All right, so 200 cos of 30 is 173. So m equals 173 newtons divided by 2.5 meters per second squared. That gives me about 69 kilograms. So that one's, you know, not asking you to find the x component first. You have to know to do that. All right. On a test, I probably would ask you to find the x and y component first. I don't know. It would depend. After determine how fast the box would move after 5 seconds of pulling. Well, I know V naught, or I shouldn't say V naught, I should say V initial, is 0, starts from rest, right? I know the acceleration is 2.5 meters per second, and I know the time is 5 seconds. So I could do V final equals V initial plus AT, right? So V final equals, well, that would be 0, starts from rest, right? So just 2.5 meters per second squared. I forgot the squared there, my bad. Times time of 5 seconds. 2.5 times 5 is 12.5 meters per second. Squared cancels. Beautiful. Determine the normal force acting on the box. Okay. So that's going to be, I should have said X there, right? I should have put X on there. In the vertical direction, the forces are balanced. So FT1y plus Fn plus Fg equals 0. All right. Well, Fg here, FT1y is going to be 200 times the sine of 30. Fn is unknown. Fg is going to be negative 690 newtons. I have to convert that. Now, I could do that side calculation if I wanted to. I could show both those here. Fg equals mg equals 69 kilograms times 10 newtons per kilogram equals 690 newtons. All right, so Fn equals 690 newtons minus 200, minus 100, right? Sine of 30 is 1/2, so Fn would only have to be 590 newtons. Now let's say the box hits a patch of stickiness and 80 newtons of friction starts to act on the box. So let's think about this for a second. So now the force accelerating it forward, right, it's still 100 newtons, right? It's FT, nope, sorry, 173 newtons. Don't have to recalculate that, is what's accelerating forward. And now we have force of friction equal to 80 newtons trying to accelerate it backwards. So F net equals MA. So it's 173 newtons minus 80 newtons equals 69 kilograms times A. So 173 minus 80 is 93 newtons divided by 69 kilograms equals A. A equals 1.3 meters per second squared. So friction really robs a lot of possible motion. All right, inclined plane problems. Got some notes here, right? Force of gravity is down, normal force is perpendicular. I actually would think of that as FGY. That one is FGX. So determine the magnitude of the skier down the hill. Magnitude, it should be the acceleration of the skier down the hill. I fixed that, and the uploaded version has that correct on it. So, oh well. So to get that, let's draw a force diagram. We've got gravity pulling this person down, so the dots represent this skier, right? Gravity's pulling them down. Normal force is perpendicular to the ramp. Okay, so the normal force is something like that. We're gonna make our axis like this, parallel to the ramp. And one thing you have to remember is whatever the angle of the ramp is, whatever that theta is, that's this theta here. Okay, so that's 15 degrees, right? So that means the FGX is what's pulling it down the ramp. FGY is what the normal force is opposing. So FGX equals mass times acceleration in the x direction. I got to do it along the ramp because that's the thing that's accelerating. So FGX is mg times the sine of theta, right? Times the sine. It's the opposite side is the x component when you're doing the inclined plane problem. The opposite side is FGX. That's FGX. That's this. FGY is the adjacent side. All right? So the m's would cancel, but I'm not going to do that yet. I want to get mg sine theta here and get a number for that. So it's going to be 650 newtons times the sine of 15 degrees equals 65 kilograms times AX. And I'm only doing that because down here I'm going to need to know what that FGX is. All right, 650 times the sine of 15 is 170 newtons. I'm going to do two sig figs on this one. Equals 65 kilograms times AX. So acceleration down the ramp is 170 newtons divided by 65 kilograms. And like we've seen numerous times now, so that's 2.6 meters per second squared. As we've seen numerous times now, a Newton per kilogram is the same as a meters per second squared. So it's the x component of gravity that's bringing it down the ramp. Great. Now let's say frictional force acts on the skier. So I don't have to worry about the normal force and gravity right now. Normal force is going to be equal to gravity, which is mg cos theta. I don't even need that though, right? We're only worried about the direction of motion here. So I'm just going to draw that x-axis, right? We still have 170 newtons pulling it down the ramp, right? And then we got 80 newtons of friction resisting. So F net equals MA is pretty much identical. So it's 170 newtons minus 80 newtons equals 65 kilograms times A. So it's very much like the previous problem. So you add friction in, 90 divided by 65 now, oops, got a syntax error, 90 divided by 65 is 1.4. 1.4 meters per second squared. So friction has a big impact on acceleration. 80 newtons doesn't seem like much, but it just cancels out quite a bit there. All right, not bad. And there was one more question on here. I didn't talk about it all in class, but this is kind of a neat one. So we've got a crate, and this one's kind of funny because this one you've probably done before, like try to push something up a hill, right? So its mass is 15 kilograms, 25 incline. It's given an initial velocity, V naught, of 3.0 meters per second. All right, and as it slides up the ramp, right, there's a force of friction acting on it. So if you look at the force diagram for it, right, here's the thing that most students would mess up. So there's Fn, here's the x-axis, here's the y-axis, right? We have force of gravity pulling it down. This is a fairly hard little question. Okay, we got force of gravity pulling it down. Now, if it's sliding up the ramp, right, it would have to be slowing down. And if it's sliding up the ramp, the friction must be down the ramp. All right, so that's kind of funny. So this is sliding up the ramp, right? If I could kind of draw like it in stages, right? It's slowing down, and then eventually it'll stop, right? The V final equals 0 meters per second. So in the middle, it'd be like 1.5 meters per second. It's losing velocity as it goes up the ramp. All right, so that means friction is going down the ramp. So we want to determine how far up the incline the crate will slide before it stops. This is V squared equation. I'm going to write that down over here. V final squared equals V naught squared plus 2 times the acceleration times however far it moves. I could call it D or delta X, either way. And D might make sense here, right? So I'm trying to find, right? That's delta X. That's M. That's V initial. I don't know why I keep calling it V naught because that's what we call it in physics. That's my fault. V initial. V initial. All right, that's friction. All right, force of friction. All right, I'm gonna call this the positive direction because that's the direction it's moving in, right? So F naught X equals MAX. That AX is needed. You need that from Newton's second law is how you get that. So we got to get A, so then we can plug it in here. So F naught X. Now this is a little tricky because we've got two forces acting in the X direction here. We got FGX pulling it down the ramp, but we also have friction pulling it down the ramp. All right, so force of friction plus FGX equals MAX. The force of friction is negative 20 newtons. FGX is gonna be, so I'll do the side calculation over here. It's gonna be 150 newtons times the sine of theta. FGY will equal 150 newtons times the cos of theta. So I'm just going to do those right out of the gate here. 25 degrees, 25 degrees. We're not going to need the normal force here, but I'll do it anyways. 150 times the sine of 25, 63 newtons. 150 times the cos of 25 is 14 newtons. Okay, so FGX is 63 newtons, and it's gonna be negative because it's down the ramp. So negative 63 newtons. They're both slowing this thing down. 15 kilograms times the acceleration in the x direction. So we've got negative 83 newtons divided by 15 kilograms equals AX. So 83 divided by 15 is negative 5.5 meters per second squared. So it's going to slow down pretty quickly. So now we can take that and plug it in over here. I'll do that calculation down here. All right, so we've got V final is 0 meters per second squared. V initial was 3.0 meters per second. It's going to be squared plus 2, slowing down a rate of negative 5.5 meters per second squared. Now, if you forget the sign here, it's just going to make a simple sign error. No big deal, really. So do the math now. 9 equals negative 11 times delta x, and I dropped the units here. When I bring that over to that side, it becomes negative 9, right? 9. This would be 9. I bring it over there, it becomes negative 9. 2 times negative 0.5 is negative 11. That cancels out there. I get delta x equal to 9 divided by 11, which is 0.8 meters. 82 meters up the incline. So that's kind of a good one. I probably wouldn't give you that one on an inclined plane. No way, obviously I wouldn't. I'd give it to you on flat ground though. I definitely would give you that one on flat ground. If I gave a block of push on flat ground at some initial speed and you knew the force of friction to figure out how far it would go before it stopped, that would be a pretty great question to ask you, and I think it would separate out some of you that watched the video and didn't watch the video.